Hello, algebra students. This is Ms. Kaul, and I'm here to give you a short little lecture on graphing roots and radicals, part of our Roots and Radicals series. So the big thing we want to tackle today is understand what the definition, or apply the definition of square root, cube roots, fourth roots, etc., the definition of our roots, to graphing these in the XY coordinate plane. So what we want to do is we want to look at things like the domain. So we're going to review that definition as we go through it. And we want to look at how to graph a variety of different radicals and applying the definition of domain and range, and some other key points we're going to make about roots and radicals. So how do we graph these in the Cartesian plane? Well, first, what we want to do is give ourselves a few guidelines in graphing these. So here's a guideline to graphing. So here's a guide, or tips, to graphing roots. And the number one thing is to try to understand what kind of values you're going to have, what kind of points you're going to have on these radicals, what you will have in your table of values. So the first thing I would encourage you to do, this is really important because it gives you a feel for what the graph will look like, is first make a table of values. With points that are relatively easy or simple to graph. Okay. So a table of values, remember, are points on the graph. Okay. And one other little note here is it's good to include intercepts if possible. So try to include X and Y intercepts if you can. Okay. The other thing we want to do is, another guide, is to look at the possible X values. Look at the domain. And the idea is to estimate its regions. You sort of want to estimate where your graph is going to exist. So a little side note, if you forgot what the domain is, just a little reminder. The domain is all the possible X values for an equation, a function, or a graph. So what we want to think of is, what are all the possible X values that we could possibly put into these roots and radicals? What are all the possible inputs? So the domain is where the graph lives along the x-axis. So domain, all possible X values. All possible X values, or slash. You could have a graph that's velocity as a function of time instead, where instead of Y and X, you have V and T. So just a little reminder. So recall, domain is all the possible X values or your inputs. Okay. Range are your Y's, all the possible Y values. So a little reminder there. So what you want to try to do is understand what the domain of these root functions are. And then the third step is just to go ahead and sketch. Okay, sketch as much as you can. Use appropriate scale. And getting a good sense of graphing really takes time. The more you do these, the more you get a sense of which numbers to choose in your table of values, which points to graph, and that will give you a better idea on how to do a decent sketch of these functions and understand them. So here are some examples. And what we're going to do in these examples that will allow you to explore what these will look like is to sketch. Let's sketch and state the domain I'm going to call them equations for now, but later we're going to learn that these are actually more than just equations. They're functions. Okay? So really the important thing that we want to be able to do is to sketch these roots and radicals and state their domain. Okay, starting with number one, we're going to start with the real basic one. Let's take a look at the equation y equals the square root of x. What this is an equation with two variables, which means that it could be plotted in the xy plane. We have ordered pairs or points that make up a picture. There's a relationship between the x and y values. Every x is paired up with a y. And we have an infinite amount of points that fit this pattern. We can put in some number for x and get a specific output for y. Put in another number for x, get a specific output for y. And that's what we want to reflect in the table of values and in our graph. So here we have an equation. With every equation, we have an associated graph representation. So every equation has its graph representation. Every equation with two variables. Okay, so this is an equation with two variables. That means that we could graph it in the xy plane. So just a few little tips a few reminders on how we do graphs. Okay, so here's our table of values. And what I'm going to do is pick a bunch of values for x that will work with this function, and then find the corresponding y coordinate so that I get the full points. So I'm just going to go ahead and pick any value for x. Well, not any value. What I want to do is get smart about what I pick. Since x is underneath the square root sign, I want to pick values that I can easily take the square root of. So let me go ahead and start with 0. And on the side, I'm going to do some side work here. I'm going to say if x equals 0, then according to my equation, my rule here, if x is 0, then y will equal the square root of 0, which equals 0. Okay? And I get the ordered pair 0, 0. Well, that one's a nice one. So we know the point 0, 0 is on the graph. Now let me pick another one. I want to pick perfect square numbers that work. Let me pick the number 1, because I know 1 is a perfect square. If I pick x being 1, then if x equals 1, then y equals the square root of 1, which equals 1. Okay, that means we have the ordered pair 1, 1 on there. All right, we have 2 points on our graph. Unlike lines, where you only need 2 points, as long as you don't make a mistake, you get your full graph. Other types of equations, functions, curves need a few more points until you get really familiar with the differences between some standard graphs like square root graphs, rational graphs, square graphs, cube graphs, etc. So what I want to do is continue on and get a lot more points. Now, you can see that these perfect square numbers are going to start to climb. I don't want to pick the number 2 because the square root of 2 is an approximation. I could use a decimal form. I'm mean, I could say, well, if x is 2, then y is going to be I'll just go ahead and add that. Then y equals the square root of 2, which is approximately 1.41. Okay, if you put that on your calculator. Not the best number to use. It's a hard one to graph. Okay, so what I want to do is, I'll leave it at 1.4 to make it easier. I want to pick some nicer numbers, some better behaved numbers, right? So let me go ahead and pick x being 4 here. If x is 4, then y equals the square root of 4, which equals 2, okay? Now this is positive, so all these roots come out positive. So remember, this gives me a positive 2. And I could go on with these. I could go on dot, dot, dot. I would pick 9 if x is 9. Then we get 3. So we have the points 4, 2 on there, 9, 3, etc. Now one more test to do here, which is a core idea behind the domain of our function or our equation in this case. What we want to do is we want to go ahead and see what happens if x equals -1. Then what happens in this case, right? So far I've only picked positive numbers and 0 here. But if I put a negative number underneath here, I'm going to try to take the square root of negative, which is a non-real number, and we can't graph those. So in this case, if x is -1, then y equals the square root of -1, and that is not real. It's an imaginary number. Okay. So anyways, in this case, we would say -1, non-real. We don't have any points there. So we could continue on with other negatives. -2 doesn't work, -3, -4, -5. So what happens, any negative number I plug into here will not give me a real output. And in those cases, we cross this out. This is not real, which means it's not part of our domain. We're not allowed to have any negative inputs in this specific equation because it doesn't give you a valid real output. Okay, so let's go ahead and do a sketch here. Sketch. Here's our sketch. And what I want to try to do is look at the trends of my table here, of my points. Okay. I want to give myself a lot of space for x. So I want to give myself a big scale for my x values. I'm going to do a 1-to-1 scale. I'm not going over above any number of 10. So I want to have a lot of emphasis in the first quadrant where a lot of the points I have on my table are located. So what I'm going to do is I'm going to go ahead and sketch this out, give myself a lot of room in this first quadrant. Okay, I'll label my axis, x, y. And the more you do these, the better you get at them. I'm going to do a 1-to-1 scale. I want to try to get up to the number 9 here, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, there's 9. And I'll label some of these so that whoever reads my sketch will understand what my scale is and will know how to interpret the points in my graph. Very important detail. Some negatives, even though I don't have any negative outputs, and some negative x's, even though I don't have any negative inputs. It just gives you a good sense of what your graph is portraying. And here I'm going to do 1, 2, 3, 4, my y-axis. So I'm going to plot some of the points I have. I have the point 0, 0 here. Then I have 1, 1. Then I have 4, 2. And then I have 9, 3. So here we go. And I could go on, right? We could go on and pick an infinite number of perfect squares, 16, 25, 36, 49, and on and on and on. And to reflect that onward infinite number of points, I'm going to join these points together I have and show this with some arrow. So we know what's going to happen is this huge climb in this direction, but our y outputs will climb a lot slower. Okay? So this is our trend, and you need to put the arrow on there because there's an infinite amount of points that work, correspondences that work with this equation, that are reflected by this equation. Very important detail. I'm going to label some of my points here. So I have 0, 0. I have 1, 1. I have 4, 2. And then I have 9, 3. Okay, those are the points I have on there. So notice, there's no negative points here. No negative x values shown on the graph, which makes sense because we don't have any real outputs. We don't have any negative outputs. Nothing I put in for x will give me a negative output. So this gives me a sense of what my graph is all about. In this case right here, what do I have? I have a graph that only has values for x that are 0, including 0 and above. And that's what my domain is. My domain is all about all the possible x values for this graph or equation. So all the possible x values this graph covers from left to right in my domain. And my domain, I would say, is using the correct notation, interval notation. I can say my domain is from the point 0, including the point 0, to infinity, which is never included, always parentheses. My range, I'm going to go ahead and add range, even though I didn't ask for it, but it helps you to practice. My range is all the possible y values from bottom to top my graph covers, all my possible outputs of my equation, my rule, my function. My range is from 0. I only have y values up here. I have this y value, this output, and then I have, even though it grows slower than the x, I have an infinite amount of outputs going upward, and that is 0 to infinity as well. Okay. Good. So this is for number 1. I'm going to label this number 1. And we're going to do another one. Now I'm going to go ahead and add a few more twists and turns. Okay, so example number 2 is to graph y equals the square root of x minus 2. And I have a lot of these exercises on the worksheet so you can compare what happens when you add or subtract different numbers into your square root, what it does to the graph. Okay. I was a coffee man. So here's my table of values. All right. In this case, I have to do a little bit more thinking. Okay. I want to pick a number for x so that when I subtract 2 from it, I will have a perfect square. This means nice output for y. Well, it doesn't necessarily have to be a perfect square, but I'm going to try to avoid working with decimals. You can really pick anything. What you do have to make sure is to pick a number for x that creates a number that's 0 or greater than that. So you want some value here to be 0 or greater. So we have to be very careful what we pick for x. So to start with, let's go ahead and make it 0, right? If we pick x to be 2, then y will be a certain output. So let's start with, if x equals 2, then y equals myself a little more space here, and y will equal the square root of 2 minus 2, which equals 0. Because that's the square root of 0, which equals 0. So here we have 0. So we have the point 2, 0 on our graph. Okay, next up. Oh, what should we pick next? Well, if I pick 3, I can see that 3 minus 2 will give me a 1, and that's a nice, perfect root to work with. So I'm going to go ahead and pick 3 next. I'm going to say if x equals 3, then y equals the square root of 3 minus 2, which equals the square root of 1, which is 1. And I get the value 3, 1 out of there. Okay, the 0.31 that will be on my graph. And then moving onward, I'm going to follow the same trend. I'm looking at the pattern. Now I'm like, let me make a 4 underneath here. What does x need to be to create a 4 underneath here? Well, I want a 6. If x is 6, then we have y equals the square root of 6 minus 2, which equals the square root of 4. And that's a positive square root of 4, and that's 2. That works out nice. So I get the pair 6, 2, and I could go on and on. I could pick next, let's see, let me try to make a 9 underneath there. Well, x would have to be 11, because 11 minus 2 will give me 9, and the square root of 9 is 3, so I get 11, 3. Now, just another thought to carry into this equation is what happens if x is 0, then we'll see that then we'll have the square root of 0 minus 2. Y equals the square root of 0 minus 2. And y equals the square root of negative 2, which is not real. Okay, just a little note there. Okay, good. So what does this graph look like? And how is it going to be different than this? I'm going to go ahead and do something where I'm going to share this on the same coordinate plane. Okay, so in this case, this is for number 1, my domain and range. Number 2, I'm going to go ahead and graph in red. I'm going to see what little difference exists between the graph we just did, the square root of x, and the square root of x minus 2. So this was the square root of x graph right here. Finding a nice spot to put it in. And this next graph is 2, 0. And then we have the point 3, 1. And then we have the point 6, 2. And then we have the point 11, 3. So I'm going to have to make another point 11, 3. And notice what's different here. The second graph right here looks like every point got shifted over 2 units. Okay, this is a topic you'll explore a little later when you put in the minus 2 here. It makes everything move over 2 units. So this is my number 2 graph right here. This is the Now, 2, what's our domain and range? Our domain in this case, everything moved over 2 units, so all the possible x values for this new graph are just including 2 to infinity. The graph lives with respect to the x-axis from 2 to infinity. So we'll say the domain is from 2 to infinity, and my range is again from 0 to infinity. And just making note of the points again here, we have 2, 0. What we have is 6, 2, and then we had 11, 3, in red. Okay, so here we have 2 graphs. Another graph we could test out. And compare, add a little variation. Let's do the graph. Number 3, y equals the square root of x minus 2. Let's see how that's a little different. I'm going to go through this a little speedier this time. My x, y table here. It's going to correlate to my inputs and my outputs, all the points that exist for this equation of this graph. So I want to pick numbers for x, in this case, that are just perfect squares again. And then I just subtract 2 from those outputs. So if x is then my y will equal the square root of 0 minus 2, which equals minus 2. So I have 0 minus 2. And then working my way down, if I pick x to be 1, the square root of 1 minus 2 is negative 1. If I pick x to be 4, so it's a perfect square, I say the square root of 4 minus 2. Square root of 4 is 2, and 2 minus 2 is 0. And then if I pick 9, which is a perfect square, I get the square root of 9, which is 3, and 3 minus 2 is 1. Okay, that's my general shred. So notice what's happening here again. And also note that I don't want negatives. In this case, I have the point, I start out with the point 0, negative 2. I'm going to do this one in green. Okay. So graphing the points that I found here is 0, negative 2, 1, negative 1, 4, 0, 9, 1, and then of course here I have 0, negative 2. There we go. Notice what that does. I have my minus 2 on the outside instead of underneath the radical sign. It just takes the whole square root graph, moves it down 2 units. So it takes the original, moves it down. The minus 2 underneath the square root moves it over to the right 2. So this is my third graph. And from here, I can go ahead and state my domain and range. What are all the allowed x values? What are all the allowed inputs? Again, it's anything that's 0 and above, as you can see from the graph. What are all the possible x values? From left to right, we're going to say 0 to infinity. And I'm going to add in the range again, just as a bonus. The range here is from above. All my outputs are negative 2 and above. So all my y values possible go from negative 2, including negative 2, to infinity. And that's how you graph that type of radical. Now I'm going to add one more. Let's do a quick cube root. And then you could explore fourth roots and more. So this shows you 3 square root functions, 3 square root equations. We'll get to the word function in a little bit. But it shows you how to graph them using table of values and exploring the domains and ranges. I'm going to do one more example with some space. That way we understand how to work with roots that are more than just the index number 2. Let's go ahead and take a look at the cube root function. And you can explore, it's a little bigger here, you could explore all the same dynamics as we did with the square root. You could add a 1 here, or subtract a 1, add a 1 here, subtract a 1, and when we start putting in other factors, we can see how these main functions change with the numbers. Okay, but let's get the basics down. So here what we want to do is do our table of values again. So our table of values will help us understand the graph x and y. And now the difference is I'm looking at cube roots, so I really want to be familiar with my cube root numbers. Let's go ahead and take a look at the number 0 is always a nice one, right? If x equals 0, then y equals the cube root of 0, which equals 0. Okay, what number multiplied by itself 3 times gives you that 0? Well, it has to be 0. 0 times 0 times 0 equals 0. So we have the point order pair 0, 0 on the graph. Now notice, x-intercept is when you let y equal 0, and y-intercept is when you let x equal to 0. So this is both your x and your y-intercept as well. Just a reminder on how you use those terms. Now, let me see, what are the roots do I want to use? I could use 1, because the cube root of 1 is 1, since 1 times 1 times 1 3 times gives you 1. If x equals 1, then y equals the cube root of 1, which equals 1. So 1, 1. With our combo. And working through, excuse me, this is not a good time to get a cough. Okay, the next number I want to pick is 8. If x equals 8, then y equals the cube root of 8, which equals 2. I pick 8 because it's a perfect cube, and we get the 0.82 on the graph. Okay, so now the question is, what about negatives? Cube roots, you could take cube roots of negative numbers. So I can use all the same values here, except with negatives. So I'm going to go ahead and try -1. This will give me an interesting graph that will be different than the domain of the square root x graph. If x equals -1, then y equals the cube root of -1, which equals -1, since -1 times -1 times -1, -1 multiplied by itself 3 times gives you that. And we could go -8, -2, and onwards. And we could add an infinity number of points. Just depends on how much time is available to you. So that should give us enough to get the essence of the graph. So let's go ahead and do a sketch. And looking at my excuse me. Looking at my values, I'm going to have a lot of x on my scale. So I'm going to spread it out far left and right and try to fit -8 there for my x.
my outputs only go from -2 and 2. I can add a few more points, but there's going to be a lot of stretch along the x-axis. That's 8. That's -8. So, what I'm going to do now is plot the points. This should be enough to get the table of value points I have. So, let's see. I have 0, 0, 1, 1, 8, 2. -1, -1, -8, -2, and then the next one will be -27, -3, and then 27, 3. So connecting all these, yields a graph like this. Okay, I gotta show the arrow because it goes on far, far, far. There's an infinite array of points. So what I want to do is label some of these. 1, 1, 8, 2, -1, 1, -1, -1, and -8, -2. And that's your cube root of x graph. So this graph correlates to, this equation correlates to this graph. They're the same thing, two ways of representing the same relationship. This is the cube root of x graph. And our domain, lastly, what we'll do is look at our domain and note the difference between the cube root of x domain and the square root. Now, we have covered every x value. This goes on to infinity this way, and this goes on to infinity this way. Excuse me. This graph covers every single possible x value. So my domain is all real numbers, or I could say from -infinity to positive infinity. My range also is, eventually this will climb down, 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 this will climb up, up, and up. My range is also all real numbers, or -infinity to positive infinity. Okay. And you could export some other variations on this, but that's a basic intro for now. All right, I'm gonna go catch my breath. Sorry about the little coughing towards the end, but we'll continue with more roots and radicals. We'll look at some other basic operations, and then we'll be done with this section. Thank you.